In our previous video, we proved this theorem. Today, we will show that this theorem is true when we have a negative value for n and also a rational value for n. So to start off, let's assume that n is equal to minus m, where m is a positive integer. So if this theorem is true for negative values of n, then we should get that the limit of x to the power minus m minus a to the power minus m divided by x minus a as x tends to a will be equal to minus m into a to the power minus m minus 1. So let's start with our left hand side here. So here what our first step should be is to change this negative power into a positive one. So for that we change our numerator to 1 over x to the power m minus 1 over a to the power m. Now we have positive powers here in our numerator. So then we can now simplify this in our usual way. So that would be a to the power m minus x to the power m divided by a to the power m into x to the power m. So that will come down to the denominator. So our next step will be to take minus out of the numerator. So that will be minus into x to the power m minus a to the power m divided by the same denominator. So then we find the limits of this separately. How we separate it is that we take this x to the power m minus a to the power m divided by x minus a into one limit and the rest into another limit. So this minus sign will be out here. Now we can see that this is in our theorem form. It is in this form, x to the power n minus a to the power n divided by x minus a. So we can use this to substitute for this. So that will be this minus into m into a to the power m minus 1. For this we use our direct substitution. So that will be 1 over a to the power m into a to the power m. So that is 1 over a to the power 2m. So now later we can simplify this as minus m into a to the power m minus 1 into a to the power minus 2m. So our final one will be minus m into a to the power minus m minus 1. So this is the answer that we expected in the first case. So this means that this theorem holds true for negative values of n. So now let's see whether this theorem is true for rational values of n. So for this we let n equals p over q, where p and q are integers. So if our theorem is correct, we should get limit of x to the power p over q minus a to the power p over q divided by x minus a as x tends to a will be equal to n into a to the power n minus 1, that is p over q into a to the power p over q minus 1. So let's take our left hand side. So the numerator we can separate it like this. So x to the power p over q can be written as x to the power 1 over q to the power p minus a to the power p over q can be written as a to the power 1 over q to the power p. So then we substitute this. So instead of x to the power 1 over q we write capital X, and instead of a to the power 1 over q we write capital A. So this means that simple x is equal to capital X to the power q and simple a is equal to capital A to the power q. So here since we made this substitution, earlier we had our limit as x tends to a. So now that will change to as capital X tends to capital A. So now let's simplify even more. So instead of this we write capital X to the power p minus capital A to the power p divided by capital X to the power q minus capital A to the power q. So now what we do is we divide the numerator and the denominator by x minus a, and also we find their limits separately. So when we do this, we will get this in our theorem form, that is x to the power n minus a to the power n divided by x minus a. So both this numerator and denominator are in this theorem form. So we can use our theorem to simplify this. That will be equal to p into a to the power p minus 1 divided by q into a to the power q minus 1. So here we can get it as p over q into a to the power p minus 1 minus q plus 1. So this minus 1 and plus 1 will cancel each other to give us a to the power p minus q. So instead of this a, now we substitute our original values, that is simple a to the power 1 over q. So when we substitute this, we get p over q into a to the power 1 over q to the power p minus q. So when we multiply this p minus q with this 1 over q, we get our final expected answer p over q into a to the power p over q minus 1. So this proves that this theorem is true even for rational values of n. So now we have shown you that this theorem is true for all positive values of n, negative values of n, and also rational values of n. Try answering the exercises given in the description below to become familiar with the use of this theorem. The answers are also given for your reference. Until we meet again, take care.